Hello, the internet, and welcome to Open Source Directions, hosted by Quansight, the webinar that brings you all of the news about the future of your favorite open source projects. My name is Anthony Skopatz, your host for Open Source Directions. Co-hosting with me today is David Charbonneau.
Hi, I'm David Charbonneau, and I'm excited to be the co-host for this episode of Open Source Directions. I lead the development of open teams here at Quansight, and I'm based in Durham, North Carolina.
And joining us today is our guest, Ralph. Ralph, you want to go ahead and introduce yourself?
Yeah. Hi, Anthony, David. Thanks for the invite.
Of course.
I'm a data scientist. I'm at FP Innovations in Canada, and I also work half of my time for Scion in New Zealand, both the forestry industry. And I'm a developer of Numpy, SciPy, and PyWavelets.
Wow, and if that's not enough of a CV, I don't know what would be. So this week, though, we'll be bringing you all tech headlines from around the world and around the internet. Ralph, what's news with you?
I read an article last week with the headline, "Is technology keeping you from realizing your full potential?" And it was mostly about, economists catching up with the times, so that, they kind of figured out that finally, when there's a downturn, usually, unemployment goes up, and then, economy goes better, and employment goes back down. And this is the first time in history where that's not the case because of technology.
Interesting.
Very good.
Yeah.
Huh.
Very interesting. David?
Yeah, earlier this week, there was a gist published by Rich Hickey. He's the main developer of Clojure, the programming language built on top of the JVM. And the headline for that gist was, "Open source is not about you." It was an interesting take from a maintainer of a project on the kinds of bad behaviors that he sometimes has to deal with, and the fallout from handling, rude or insensitive comments about projects and how they're run and their directions and such. And it was interesting to see the discussion that sparked. In particular, I saw one post that was sympathetic to people who have, complaints or worries, and he was basically stating so much of what he does is built and depends upon open source that, without the ability to say, pay for something, it's difficult to figure out who to talk to, how to talk to them, etc. So I think hopefully that's the beginning of an interesting conversation.
Yeah, thanks very much for sharing that, David. You shared it with me earlier this week, and I thought it was a great read, so be sure to check that out. For my part, this week, Project Phi changed its name to Google Phi and is now also available on a much larger set of phones, rather than the 6 that it had supported previously. This is the only cell service I've ever truly loved, and I highly recommend that you check it out. And we'll link to a Ars Technica article about it in the show notes. So yeah, that's our news for the week. So let's go ahead and dive in to our project introduction. So the SciPy library is one of the core packages that make up modern scientific computing in Python. It provides many user-friendly and efficient numerical routines, such as routines for numerical integration and optimization, and it has about 5,000 stars on GitHub currently, a little more than that, and almost 700 contributors. SciPy has about 2.6 million downloads from anaconda.org alone. There's probably a lot more than that on PyPI and etc. So it's a very popular, long-running project that's been around for decades. I think it's a fair statement at this point. Yeah, we're going to go ahead and ask a few questions of you, Ralph.
So Ralph, why was this project started?
Well, it started back in the time when there was Python, and there was an array object, and there were a bunch of people doing science with it, but there was nothing else. So it basically was to provide a library with lots of fundamental algorithms for doing science with.
Fantastic.
And what need does SciPy fill?
Well, I'm gonna say something odd, but it's like the standard library for scientific Python, I would say.
Yeah.
And unlike the real Python standard library, code does not go there to die. But anyway, it's similar. It's used all throughout science.
It's the Boost C++ of the Python.
Something like that.
Something like that, right? Okay, maybe not a perfect analogy, but
Well, given that you said it's a standard, are there any alternatives out there?
I think there are alternatives for parts. So, for example, you have SciPy.stats, and you have an alternative in stats models, but it's mostly complementary. Like stats models has way more advanced statistics and econometrics models, and the same for SciPy.ndImage. There's image processing, and then scikit-image has a lot more. SciPy.signal has Python control, that does similar with things like finite impulse response filters. What else? SciPy.cluster, that's scikit-learn has a big superset of that.
yeah.
But then there are many other parts that there's just no replacement for, like all the linear algebra, all the special functions.
Awesome. So what technologies is SciPy built upon?
So it's going to be a long list.
That's fine. Yeah, that's fine.
Just in terms of programming languages, so it contains Python, Cython, C, C++, and Fortran, which is hairy. That's why we have so many build problems. And then we have APIs in mainly Python, but also we have Cython and C APIs.
Right. So are there other, since that's just the programming languages, are there other like libraries that you link to as well, or in those languages, or what kind of drives the need to be so polyglot?
What drives the need? Mainly having to use like 30, 40 years of numerical algorithm development history that most of those Fortran libraries, we would love to just have a C equivalent, but there just isn't one.
Right.
And it's just not feasible to go and rewrite all that code that has been battle tested for 30 years.
Right.
In terms of what we link to, mainly NumPy, and then one of the BLAS and LAPACK libraries. So there can be OpenBLAS or MKL or Atlas.
Right.
Or some more esoteric things.
Great.
So who started SciPy, Ralph?
So it was started by 3 people. So Travis Oliphant, Eric Jones, and Priyaru Peterson back in 2001. And they are no longer involved. They have been until, I think Travis was involved for the longest, until 2010 or so. And he still, pitches in an idea once in a while, which is good. But yeah, it's a much bigger team now.
Right. As to that team, who maintains the project? Who maintains SciPy?
Well, that's a big team effort. So we have, for every release, we have about 120 unique contributors. We have,
that's impressive.
In total, 36 people with commit rights, about half of whom are active regularly.
It's pretty good.
Yeah. What communities are users and contributors coming from?
Where are they not coming from? It's basically, almost any discipline of science. And outside of that, the data science community, it's used in a wide variety of industries. I mean, for myself, like, I worked in the semiconductor industry. I worked in research on medical imaging. I worked on forestry, and, it applies everywhere.
Excellent. Is the project participating in any diversity and inclusion efforts currently?
So we are an affiliate member of NumFocus.
Okay.
And they have a specific diversity and inclusion initiative. So I very closely follow that, and we try to do everything according to best practices. So we spent a lot of time last year, writing an improved code of conduct. And we were pretty happy with the outcome of that.
Right.
I think, in terms of the diversity of the contributor, user and contributor base, I think that's very diverse. But in terms of maintainers, we would like to see a bit more. I think we're doing pretty well in geographic diversity, but especially in gender diversity. We only have out of those 36 people with commit rights, there are only 2 women.
Yeah.
And they're both not active right now. So it's something that I would really like to see improved.
Right. Yeah. So there's work to be done and outreach to be done. And
Oh yeah, for sure.
NumFocus is certainly helping guide everyone in that towards more inclusive communities. So that's great. So at this point, we're going to go ahead and shift, now that we've done a brief introduction, to a project demo and walkthrough section. So I believe, Ralph, you've got some demos you can show us. So, this helps to really, now that we've contextualized SciPy, to see where and how SciPy works as a library and what it can do. So what do you want to show us first?
All right, so let me see if I can share my screen here. All right. Hope everyone sees that. Wait. No?
It's not up and running yet. First rule of live demos, right?
Try it again.
We swear this worked in the practice. So.
Yes, it did. Yes. It tells me you must allow Livestorm to steer your screen, and it does not give me a button. Interesting.
Okay.
Is it up in the top, maybe?
Fun.
We also have the links to some of these, so we can throw those in the...
We'll give you one more moment, I guess. Otherwise, I've got the docs open, and I could try to display while you guide me through it.
Yeah, David, why don't you go ahead and open those things, the links up, if you want to share your screen.
Yeah, maybe try that.
All right.
Go.
Let me pull this out.
There we go. Yeah, so I thought I'd start with the documentation because just to give a flavor of what's in there, especially if you scroll down to API reference.
Let me make this a little bit smaller so it'll be bigger on people's screens. There we go.
Yes. All right, now that's readable.
Docs are always a good place to start. So
basically, there's one entry per SciPy submodule. So SciPy is divided into, if I counted correctly, 16 submodules, and each of them is kind of independent from the other. They might use each other under the hood, but they're usually a completely different topic. Right. So cluster is about clustering. Well, constant is very tiny, just constant you use, like size of the sun, Planck's constant, that kind of thing. And then it keeps on going like that. And I can't really demo all of that, so I thought I'd just show it, and then I pick a couple of examples that just show the type of thing you can do with it.
Yeah, makes sense.
So
let me copy this link here, and I'll open up one of the notebooks. I guess this is the documentation.
Yes. No, that's not the documentation. So, but in addition to the documentation, we have a thing called a cookbook that we don't really, maintain or, review as strictly as the documentation. So basically, everyone who has an interesting example can just throw it up, and as long as it runs and it looks fairly reasonable, we just merge it, and
awesome.
it's a nice way to share like relevant, like kind of worked examples. So I picked one here, nonlinear regression, which I needed recently, and I actually forgot that SciPy did this, but it turned out to be very easy. So maybe if you scroll down a little bit further, we'll skip the explanation of what nonlinear regression is, because I'm guessing most people know that. A little bit further. Yeah. All right. To generate data, let's start there. So basically, there's just a function that generates data, which is a damped oscillation, right? So it's an exponential term times a sine, and then it adds some noise on top, and it adds some outliers. So the next cells basically define T train and Y train. And that cell below, yes. To generate that data. And then we need a simple function to kind of fit the data. So that's the same function used to generate the data, but without any noise. Right, so that just has a few parameters. That are the parameters we're going to try and fit. Now, if we want to try and use SciPy for this, the import always looks like from SciPy.submodule. So in this case, from SciPy.optimize, import the function that you want. And then if you do standard regression, there's just a function least squares where you pass in the function, you pass in some starting guess. Which in this case is just a bunch of ones, so it'd be way off from the actual answer. And then the arguments.
And this is using a Fortran library, right, to actually run least squares. Is that correct?
I think this one actually isn't. Most optimizers, that the older ones use Fortran, but this one is a bit more recent. It was written in the GSOC a few years ago.
Okay. Yeah. I remember the old Fortran ones, and it just totally blew my mind at the time in like 2006 that you could write a Python function and then have it go all the way down to Fortran and do an optimization and come back up. So, yeah.
Okay.
Yeah.
But this, this result least squares. So we'll plot it in a minute so you see what it looks like. In order to now do robust linear regression, that basically means ignore all the outliers in the data, or treat them differently so they don't really skew the result. All we have to do in this line is basically add a loss function. In this case, it's a soft L1. It's one of 5 or 6 loss functions available in this function. And that gives us a robust linear regression result. And then if we plot the result, then you'll see the difference. Yeah, there's the plot. So we've got in green the true answer, and in light blue, the robust linear regression result, which is almost correct, while the red one is, the regular least squares type fitting, and it's way off clearly, skewed by a couple of these big outliers. Yeah, so this is just one example. I had a couple more. So that's in the other notebook, David.
Yep, it'll just take me a moment. Copy this. Here we go.
Yes. So I first picked another kind of something you need in very many sciences, which is differential equations, integration of differential equations. So we've had that, and Anthony, if you're going to ask the same again, also this is not Fortran. It's again,
yeah.
Again, the old stuff is in Fortran, and this is a new function that was written last year, I think, maybe 2 years ago.
Cool.
That has just a nicer interface for this. So the way this works is to from SciPy import integrate, define a little function, and this function is a differential equation. So it's set 2 differential equations, one for the growth rate of rabbits over time, and the second the growth rates of foxes, which hunt rabbits. So basically, if there's a lot of rabbits, the foxes will grow faster, and vice versa. It's a classical problem in systems biology. So we define some times under that, with lint space. We're going to do this for 15 days or weeks. I don't know, just 15. And we start with 12 rabbits and 6 foxes. And then we use this solve IVP. So solve initial value problem is what that stands for. And so we start with initial values only, and then we integrate this over time to find the answer at all the times you're interested in. And then if we, plot that, then you'll see, first the rabbits start to grow. They like to make babies, and at some point, that makes the foxes grow, and you get this oscillatory behavior. So again, a fairly straightforward example where you can just with a single function solve a fairly complicated set of equations. And then the last thing I want to show was something that's actually probably not in the SciPy that people have installed or in Subsystems right now. This will be in the new 1.2.0 release, which will come out probably in 2 weeks.
A little teaser.
Well, I have two in there that are already out there, but I'm also showing two new ones which are only in the newest release. And that's because global optimizers have, for as long as I can remember, have been really a pain point. When I started, there were a couple of global optimizers, and they were all terrible. and they slowly started getting better over time, and now we're at the point where I say, like, they're actually really good. They're probably close to state of the art.
Awesome.
So I'll first explain what it is. So we'll use a function here called the egg holder function, and it's plotted below there, and it's called obviously the egg holder function because that looks like a fancy egg carton. And so global optimization, the goal is to find the lowest point in that function, and that's not always easy because you need to start at some point and you need to evaluate what the value of the function is, and then you just need to start moving around. And when you have lots of minima, it's hard to find them all and then figure out which one's the actual global minimum.
So this is a very hard problem. Traditionally.
Yes.
Yeah.
So I have a couple of functions. One of the new ones is called SHTO, and it stands for, it's a graph theoretic thing. So it stands for simplical homological global. Complicated name, that's why we abbreviated it. So all you have to do is you pass in the function, and you pass in bounds on which you want to surge. So in this case, I use like -512 to +512. So that's the part you see in the plot. And we'll store the results from now in a dictionary because we're going to do this with a few global optimizers and then compare all of them. And you see what it returns, the function value that it found. So lower is better. The message whether it worked, how many function evaluations it did, and and X, at the bottom, the point that it found. So that is what it says is the global minimum.
This is really cool. This is amazing.
Yeah, and it's nice that most of these work as a single line, and they have almost the same interface.
Yeah, that's awesome.
The second one, it has a second method, the non-default method, which I think is non-default because it uses a little more memory and is not mathematically guaranteed to work in all cases. But in all my testing, I found it works even better. And the nice thing about this is, you see below, it returns a lot more results. It actually tries and find all the minima and tells you all of them.
Very cool.
All right. And then if you go down, we'll still do the same with a couple of other optimizers. So the second one is dual annealing, which is like a fancy version of simulated annealing, which is a very classical algorithm, and one that we had a really, really bad implementation of a few years back, and then we threw out. And then the same for differential evolution, which has been there since SciPy 0.15, I believe, and then Bayesian hopping, which is the first one that was actually had acceptable performance, just from SciPy 0.12 or so. So, okay, we've got now 5 different results, and we can just plot them all on the map. So there's a bit of matplotlib wrangle here to get a nice map.
As always.
Yep. So this is the same function, just now in in a 2D, so it's seen from above. So darker is lower function values. And what you see is, yellow is Bayesian hopping. Here is it's found some minimum, but it's clear it's not dark black. It's not close to the best minimum. And then we've got, here's dual annealing. Well, that looks close to a real minimum, but actually the one on the right here, the right, no, so okay. So that white one is differential evolution and the default method of SHGO. And then the plus, like right in the corner there. Yep, that one. That's the one from the Sobol sequence. So that's the actual I checked. That's slightly lower, but all three of those are pretty good. But the one you're pointing at now is the actual global minimum. And then the red dots are, all the other ones that the Sobol sequence solver found.
Oh, the local minimum. Yeah.
All the other local minima. So that seems to be working pretty well, and you can switch solvers with basically a single line of code.
Right. Very cool. Those are some excellent new features to be looking forward to in the next release. I think with that, we'll have to end our roadmap discussion, but if you have any questions about any of that, please feel free to ask and we'll get to them towards the end of the episode here. And at this point, we're going to transfer and talk about the roadmap discussion. So into our roadmap discussion. So this is kind of the meat of the episode where we dive into the relatively new SciPy roadmap, which you can see either on the SciPy docs or you can go find a fancy brochure version at quansight.com/projects. So the idea here with our roadmap discussion is that these are places where new contributors can come in, or if people want to contribute, they can come in, and these are places where the project is looking for sort of support. So that's either in code contributions or perhaps in funding. There's in various different ways. This is the direction that the project is going. So we'll get through the first 3 or 4 bullet points in detail, and then we'll maybe split off and cover some other ones that if we have time. And so I think the first one in our discussion here is going to be the evolution of BLAS and LAPACK support in SciPy, sort of in terms of library support and support for newer LAPACK features. So Ralph, did you want to take us on a sort of start us off on a discussion of that particular roadmap item?
Yeah, and maybe before I should say we actually have we just split the roadmap into like a detailed roadmap, which has per submodule like 3 or 4 ideas. So if you're a contributor and you're like, say you're just, you're a statistician. So that's really right? Then you just want to go to the detailed roadmap probably and look at scipy.stats and say like, oh, what are the top 3 or 4 ideas for stats?
Yeah. That detailed roadmap is amazing. There's a wealth of information there. It's like 9 pages long. It's great. So.
Yeah. But what we're talking about here now is like, basically the biggest ideas for SciPy overall.
Right.
So the first one is this BLAS and LAPACK. And I think it's one of the most important things that SciPy provides, because basically that's what you need to do linear algebra. And, anything we do in numerical computing, somewhere usually uses that. Right. So there are many other libraries like scikit-learn, like stats models, etc. They all use SciPy's provided BLAS and LAPACK interfaces.
Right.
So I think that's why this is probably highest on our roadmap.
Can you mention like just very briefly how SciPy's linear algebra support differs from NumPy's linear algebra interface, and why SciPy's is better, let's say?
So NumPy provides a small subset of what SciPy provides, and it has a numpy.linalg module, and the reason is historical mostly, but it's like that's really important. Some of that should be in NumPy. But in the end, most of this stuff is written in Fortran.
Right.
And NumPy cannot rely on Fortran. So what we did for NumPy is take that Fortran code, basically translate some of it to C with some automatic translator, and then stick that in. So it can do that, or it can actually link to, if you have a precompiled binary, like OpenBLAS or MKL, it can use that.
Right.
So in that case, SciPy and NumPy will actually be using the same functions. So there won't be a performance difference in those cases. and it's just that SciPy is a much more comprehensive coverage.
Right. So the bindings of these two libraries are much
Yes.
better in SciPy.
And the other thing is SciPy also provides Cython bindings for all of that.
Okay.
That doesn't at all.
Yeah, NumPy can't really do that either. So.
Yep.
The next item on the roadmap mentions sparse arrays. Can you give us a bit more background on what kind of support you're looking at there?
Yes. So sparse arrays are basically, arrays with mostly zeros. And if you store all those zeros, it gets really big. So there are specific data storage formats that kind of hide all that and have a compact representation.
Mm-hmm.
So the SciPy has always had sparse matrices. They basically act like numpy.matrix, and that's something that basically no one should be using anymore. Most people aren't using anymore, and NumPy wants to get rid of numpy.matrix at some point.
Right.
So,
so that you'd come up with something to replace that capability.
Yes.
With something other than the NumPy matrices.
Yeah, and so there's a new project called PyData Sparse. So that's kind of an in development replacement that provides us a sparse version of a NumPy array. So it's not yet done. So it needs still a couple of storage formats. But at that point, we want to adopt it in SciPy. And then SciPy also has two other modules that rely on sparse arrays or matrices at the moment. So we have sparse.cs graph, which are graph algorithms. And there's sparse.linalg, which is linear algebra routines specifically for sparse data structures. So we basically need to, finish that PyData data structure, and then adapt both linalg and CS graph to use that in addition to the sparse matrices. So the sparse matrices aren't actually going to go away because they're very widely used. Like scikit-learn relies on them fairly heavily, for example.
Oh, I see.
So we're gonna keep them, but we want to encourage people in the future to use arrays because that just plays nicer with other code that already works with NumPy arrays.
So this sounds like a fairly easy and obvious way for people who want to contribute or fund development, where they could kind of plug in and do a lot of work on SciPy with the sparse module, either inside of SciPy itself or through PyData sparse. Is that sort of a fair statement there?
Yes.
Figuring out all the integration stories. Yeah.
It's pretty clear what has to be done. It's still quite a lot of work.
Right.
But yeah, no, and there'll be big benefits, I think, for if you're using sparse arrays, then all of a sudden that will then work with a lot more code.
Right, and so the difference here with the sparse arrays is they really are n-dimensional sparse arrays, right? They're not just limited to 2 dimensions like a sparse matrix is.
Yeah. The matrix is only 2 dimensions, so this will be n-dimensional. So it will basically do whatever a NumPy array does, except for operations that don't really make sense, given the properties of sparsity.
Right, and so what are the formats, just out of curiosity, that are missing that SciPy or that PyData sparse would need to implement?
The main thing is a compressed storage format, so they're called CSR and CSC in SciPy.
Yep. Okay.
So that is still missing. So I think there's first thing on the roadmap of PyData sparse. Actually, I saw PyData sparse just got a roadmap like 2 days ago.
Yeah, they did. That's right. Yep. So you can go check that out too.
Yep.
I believe it's in the docs now. So
fantastic.
Yeah, great. David, any other questions on sparse here?
No.
Right.
Thank you.
So the next roadmap item is our Fourier transforms. So if you want to lead us down the Fourier transform story here.
Yes. Yeah. So Fourier transforms, they have been in SciPy, basically in its current incarnation since the beginning. And it's also written in Fortran. It's hard to understand code. Like it kind of works if you just want a regular Fourier transform. It's not performance-wise very optimal.
Mm-hmm.
Like it really depends on how long the arrays that you pass in. For example, if you pass in an array that has the length of a prime number, it will take forever to find you an answer. So there are algorithms that can deal with that, but SciPy doesn't have those. So it kind of, the solution time kind of shoots up very quickly.
I see.
So there's now a new library called Pocket FFT that the author of Pocket FFT just opened a pull request to add that to Numpy. Because again, like part of FFTs is duplicated between SciPy and Numpy.
Okay.
Same story as with linear algebra, basically. But we want to also put that into SciPy. So then we have like that, prime number issue goes away.
Right.
It's more accurate as well, the implementation. So that's the first one. We basically take all of the FFT functions that we have and replace them in a completely new implementation.
Excellent.
After that, there's one more big thing to do, I think, and that is to implement a backend system. Because right now there's various other libraries that provide Fourier transforms. So there's PyFFTW, which we can't really use directly in SciPy because it's GPL licensed, but it's a very high quality implementation. And then MKL has FFT functions as well.
Oh, interesting.
Basically, both of those projects, they kind of they just monkey patch SciPy, basically.
I see.
And that's not a good situation. That leads to weird and hard to understand bugs. So if we can provide a backend system where we can just say like, hey, use MKL or use FFTW.
Right. Register your FFT functionality here.
Yeah.
And then the user can just transparently choose which one he wants to use.
Yeah, that sounds great. So with Pocket, is that written in C then?
Yes.
Okay.
And I think it's at the moment on hold for maybe another month because it requires C99.
I see.
Which is allowed in Numpy, after the next release.
Gotcha. Yeah, funny how those compiler things creep up on you 20 years later. Excellent. So again, yeah, this sounds like another great place where if you're interested in writing a backend system or getting support for a backend system with some money for Fourier transforms, then this would be the place to plug in. That's awesome.
So another item on the roadmap is support for distributed arrays and GPU arrays. Is this new capability you're looking to develop or existing capability that you're looking to improve?
No, so that's actually really new, and it's the first time we put anything like that on the roadmap.
Mm-hmm.
And basically, the idea is the following: so SciPy itself is not, requiring distributed or GPU arrays, and we don't really accept code that needs, that's written for, working on distributed systems or on GPUs. Right? So there are lots of other more specialized projects that does that.
Mm-hmm.
But right now, what's going on in Numpy is basically they're splitting their API from the execution engine. So what is going to happen really soon is that you can say, hey, I write a function which uses just Numpy array interfaces, right, or just methods, and at that point, you can, let's say you make a GPU array like QPy.
Mm-hmm.
And QPy can basically register, let's say register that they can execute NumPy, function calls.
And for viewers who don't know, QPy is the NumPy implementation on top of CUDA, so on the GPUs. Yeah.
Yes. So at that point, to SciPy functions, they will look the same. So SciPy can still, the code can be unchanged. And SciPy can just be using NumPy functions, but if the user says, here's a QPy array and do it with that, it will just not it will work, it might work. We haven't actually tried this yet. So we're very curious to figure out to what extent this is going to work. And not all of SciPy will be relevant for distributed execution or execution on GPU, but some parts definitely are. so investigating this and then solving some simple bottlenecks. Maybe it might be in some cases a method of using, an ND array method rather than a function. But as
Right.
long as SciPy code can still use NumPy, but if it will work with distributed or GPU arrays, that would be awesome.
Right. That sounds like a huge effort and definitely something
Yeah.
where a lot of hands and potentially funds will come into play to help make sure that all works. I think we're running a little low on time for continued roadmap discussion, but just very, very briefly, some other things on the roadmap are improving source builds on Windows, which I know lots of people would love, particularly lots of users would love, especially on Windows. There's linear programming enhancements, improved benchmark systems for Optimize, which would be amazing to have for further improvements to that. It's always very difficult to know whether changes you've made and optimization routines are worth it or good or bad. So a benchmark system there would be amazing. Do you have any very brief comments, Ralph, on any of those or any other roadmap items?
Yeah, so we do have a benchmark system. We just, and it works pretty well. We just wanted to make it easy to use because right now it's almost impossible to figure out, how to use it, and it will take like days to run if you want to do the full thing. So it's kind of hard to. So if we want more, more people contributing optimizers, making that easier would be quite important.
Yeah,
exactly. And the source builds, I think, if we had had a roadmap back in 2010, that would be the first thing on it. It's gotten a lot better over time, but it's still way harder than it really should be.
Right.
And I think even maintainers, really struggle to build on Windows.
Yeah. Well, I think that will wrap up our roadmap discussion then, and thanks Ralph for going through this with us.
Thank you, Ralph.
Again, you can go and find the roadmap on the SciPy documentation and the more detailed roadmap on the SciPy documentation, or if you want to find this overview discussion with some short descriptions of each of these items, you can go also to the brochure at quansight.com/projects. And these are all great places where people can jump in and contribute code or funds. So that being said, it's now time for our Q&A section right before we leave here. There's a few questions that we had sent in on Twitter and one or two asked just right here in the webinar itself. So David, you want to take the first question, please?
Sure. Prakar Mahotra asked, I have experimental data to which I'm trying to fit a curve using univariate spline in SciPy. I was wondering what other curve fitting options SciPy might have. I'm relatively new to SciPy.
Oh, yeah, that's spread over quite a few modules, actually. So I showed earlier like the least squares, for example. So that's an optimize. There's a couple of other functions in optimize that do this. Like there's a function called curveFit, which is kind of, does the basics. And there's various other optimizers that you can use. Then there's in stats, if you want to fit distributions, like probability distributions, you can do that with SciPy.stats. There's also a linear regression functionality in there. And then there's a whole module called ODR, which doesn't get a whole lot of use, but it's quite powerful. It stands for orthogonal distance regression. So that's if you have data that has error bars in X and in Y, it can take both of those into account.
Very cool. Yeah, thanks. So for our next question, we have, can the solvers in SciPy deal with complex values, i.e., imaginary, quote unquote, or complex numbers? I'm specifically interested in using Nelder-Mead type minimization functions.
So technically no, but I would say, that's not a very well-defined question, because when you're using optimization, you're comparing two things and you're going to try and find the smaller one. But if you compare to complex numbers, what are you really doing? Are you comparing the magnitudes or the angles or just the real or imaginary parts? So what you should do is, basically map your complex function to a single number, right? Which could be the magnitude, and use those magnitudes, and then you can feed them into any optimizer.
Right. Makes sense.
David Brockert asks, I think SciPy has been traditionally targeted at solving engineering problems. With the rise of ML and AI, did you see people trying to use SciPy within TensorFlow or PyTorch or anything else?
Um, so, good question. So at the moment, I think I see it used in ML workflows quite a lot, but it's mainly for utility things like resizing images, etc. Like if you want to train a neural network, all the images need to be the same size. It's not used in the parts of, let's say, TensorFlow or PyTorch that do the heavy lifting, because that happens normally on GPUs. Although we'd be very interested to see like the thing we just discussed with GPU arrays. If SciPy becomes capable of handling those, I think usage might increase a little.
Very cool. Christoph Dial asks, what fraction of SciPy functions can use multiple CPU cores? Is OpenMP used for that, or is there some other technology used under the covers?
There are not that many functions, although everything that uses linear algebra, typically the linear algebra libraries split things under the hood and they use all the cores that are available. There's some functions like the KD tree implementation in SciPy.spatial and the differential evolution optimizer where you can explicitly say how many cores you want to use.
Right.
And it doesn't use OpenMP. We kind of forbid OpenMP because it's not portable enough. So it uses, well, at the moment, it uses just multiprocessing. But I think we want to switch to joblib or Loki because they're kind of more robust implementations that use multiprocessing still.
Right.
David Brockert asks, you mentioned distributed SciPy. We've seen Dask integration in several libraries, NumPy, scikit-learn, Xarray. Would a Dask SciPy make sense?
Yes and no. So what I just talked about with the sparse and distributed arrays, with QPy as an example, Dask would be the example for distributed arrays. So, and I think, there'd be a lot more of SciPy that should work distributed than that should work on GPUs. So that's definitely a focus. But a specific project, Dask SciPy, I mean, that sounds like there have been various Dask / dash something projects, right? And it usually requires like rewriting parts of the original project. And that's especially what we want to avoid. So, with this whole, the thing with the NumPy interface that I talked about, the whole goal is that we can feed in things like Dask arrays. So as long as they act like a NumPy array, things should just work.
Yeah.
Without having to rewrite anything. So I hope we won't see a separate Dask SciPy project.
Right. Oh, and it looks like we have an 11th hour question right here. So Christopher Dial asks once again, are there any plans for a SciPy 2.0, or will likely be 1.x and backward compatible in the next years?
So we spent 16 or 17 years getting to 1.0, so we're not yet thinking about 2.0. But it doesn't mean that we maintain strict backward compatibility for absolutely everything. The philosophy of SciPy, and that doesn't apply only to SciPy, but also to NumPy and most of the Python ecosystem, is to gradually evolve. And so we keep on deprecating things and then leaving them in for a few releases, showing users warnings, and then giving them advice on how to switch.
Right.
So, we don't really, if we want to do a 2.0, maybe we will, but maybe it's for marketing reasons. It won't be the same thing as for Python 2 to Python 3, where all of a sudden we kept lots of things unchanged for a very long time, and then in SciPy 2.0, all of a sudden we change everything and make it really hard for users to go from 1.9 to 2.0. We will never do that.
Right. It's a move slowly and don't break things philosophy. So
yeah, it breaks things.
yeah. All right, so at this point, we're done with our Q&A section, and we're going to move on to our world-famous rant section, where we each get 15 seconds to rant about whatever topic we want. Ralph, it is your soapbox.
Okay. So I want to rant about Conda. So Conda is awesome. It solved all my packaging worries almost. But each time I use it, like every other time I use it right now, I want to say Conda installs some pure Python package, and it insists on downgrading my NumPy, SciPy, scikit-learn, and like all of it. And it keeps on doing it. It's been doing that for the whole year, and I heard a rumor that it will be solved soon, but for now, it annoys the hell out of me.
Yep, good feedback for the Conda folks. David, your soapbox.
Cell phones. I have to switch carriers because of poor coverage with my current carrier, and they had great deals, but the great deals mean that now I'm going to have an iPhone for the first time ever, and it's a little bit against my will, but that's okay. The buy one get one was just too good to pass up, given a family of 4, so it's what it is.
Right. For my rant today, our basement flooded this weekend when we got home from Thanksgiving, and it prevented me from submitting a last-minute tutorial to PyCon on Monday. Needless to say, I am quite upset at water at the moment. That's all the time we have for today. Thanks for watching. Thanks for listening. You can find us on Twitter at Quansight AI. If you are interested in funding open source projects, including SciPy, you can find all of the project roadmaps at quansight.com/projects. Ralph, where can people find you and SciPy?
Well, on GitHub mainly. You can also just email me at ralph.commerce@gmail.com.
Excellent. All right. Well, thanks again, everybody, and join us again next episode for a cool discussion on Data Shader. All right. Bye.
Thank you, everybody.